Okay, and this behavior of the system with different frequencies of input signal will be represented by, frequency um, frequency response. We call it frequency response. Okay, and we use G J omega in order to represent to model it. All right, and we can use the um, um, we can use the magnitude and phase diagram in order to draw to represent the G J omega on the S plane, or we can use and that means we combine both magnitude and the phase of the G J omega in one diagram. Okay, and the other ways to represent the frequency response is the to draw the magnitude and the phase of the G J omega in separated axle. Okay, in separated axle, and in the magnitude diagram we use the logarithm scale. Okay, in order to the one reason why we use the logarithm scale instead of linear scale is the because the power of the signal will proportional to the square value of magnitude of the signal. Okay, that's why we have here 20 logarithm of magnitude. Okay. And we call this diagram with two axes, one for magnitude and the other for the phase. We call it both diagram. Okay, and we already form the diagram for some cases. The first one is when the G S equal to K, that means it's just a amplifier. Okay, and the other one is then you see that here on the board diagram the amplitude is just a line, a straight line. Okay, and the phase is always 0 or minus p, right? Depend on the sign of the value k. And the second phase example we already do is the first order system. Okay, GS equal to 1 over 1 TS plus 1. That means we have G J omega equal to 1 over 1 plus T J omega. And we see that the magnitude of that means the magnitude diagram will be L omega equal to minus 10 of logarithm of 1 plus t omega power 2, right? And we see that, okay, when the omega goes to 0, then the L omega will equal to 0, okay, and when the omega go to infinity, then the L omega will be approaching the line with the function with the equation of minus 20 log omega plus log t. Okay, that means we have here there are two two straight line. Okay, two straight line. That the L omega will be two straight lines. The first straight line with which is L omega equal to 0, and the other is L omega equal to, the other is the L omega equal to minus log t. Okay, minus log t line with the angle of minus 20 decibel per decade. Okay, then the real L omega will be asymptotic asymptote approximation of this straight line. Okay, and we also see that right, and we here I will try to form the one more example here. Okay, for example, we have the we have the GS will be equal to 1 over 1 plus T1S 1 plus T2S, right? And we see here in last week we already say that, okay, the L G omega here, this G omega G J omega will be built up using this form. Okay, that means G J omega will be equal to 1 over 1 plus T1 J omega 1 T per with 1 plus T2 J omega. Okay, and then we will have, the L omega will be equal to what is this here. Okay, this equation here, L omega will be equal to sum of the L omega of the nominator polynomial minus sum of the L omega of the denominator polynomial. Okay, and here we have because the amplitude here is equal to 1, that means the logarithm of 1 is 0, so we have L omega will be equal to, you know, minus okay, here minus 20 log of module of 1 plus T1 G omega minus 20 log of 1 plus T2 G omega, right? And this one we already have from the previous example here, you see here, right? That means it will be equal to, you know, okay, will be equal to minus 10, sorry, minus 10 log of 1 plus T1 power 2 omega power 2, right? And this one is also the same procedure. Then we have here equal to, yes, 20, not 220. Okay, minus 10 logarithm of 1 plus T2 omega power 2, right? Here 10, right? And when we draw it on the both diagram, okay, and the phase is the okay, and the phi omega is equal to here we have the equation over there, where is the phase? The phase is the sum of the phase. That's the phase of the system. The phase it's a minus octane. Okay, and the phase phi omega, okay, will be equals to the phi 1 omega plus phi 2 omega, okay, and the phi 1 omega, where the phi 1 omega will be equal to minus r tan of T omega, right? And the same as this one, we have phi 2 omega will be equal to minus tan T1 and T2 omega, right? Okay, and we also have here when the omega goes to the near to the zeros, then we have the T1 and T2 equal to 0. Okay, and when the omega goes to the infinity, then we have the T1 and T2 equal to minus P over 2, right? P over 2 here is the same as this one. Okay, and yeah, so now we try to draw the both diagram of this system. Okay, and here I will draw the axle for the L omega, and we suppose that T1 is smaller than T2. Okay, then here, for example, we put it on the on the diagram. Here we have the here is will be 1 over T1. Okay, and here will be 1 over T2. Sorry, T1, when the T1 smaller than T2, then here should be T. Okay, I will try here T1 greater than T2, right? All right, then now we see, first we draw the L1 diagram. Okay, and here we draw L1 omega, and here we have L2 omega, right? Then we that means here we check the diagram addition. Then we draw first the diagram for L1 omega. It will be, it have two asymptote line here, yes, and here is minus 20 decibel, and for the yes here, okay, and for the second L, and then here will be the real and we call it here L1 omega. Okay, and the second one will be the same here. This color is this. No, this color is hard to see. So the second one we have here, and the same as we have the same angle here with the minus 20 decibel per decade. Okay, and the real diagram will be here. What is this? Okay, then now we combine these two lines, these two here is L2 omega, and when we combine these two branch of the axle of the diagram into one, and we have the final one. Okay, so the final one should be, you see here, first it come to the same, and here will be it will add with another 20 decibel per decade lines, and we have here the second one will be 20 decibel per decade here, right? And you see the real one, oops, the real one will be like this. Yes. Okay. That means we have here the first part of the final. Here we have the first part. We have the 0 dB per decade. Okay. And the second part here we have minus 20 dB per decade. And the last part of the diagram here we have here, because we have the minus 20 plus minus 20, so we have here minus 40 dB per decade. Okay, and the red line here will be the final. This one is L omega. Okay, and if we draw the diagram for phi, it's also the same situation. Okay, here we have diagram for phi. We still have these two frequency. Okay, the two frequency here. This one here. Right, and the first one we will have, you see here, suppose we have here minus p over 2, and then here we will have minus p, right? Then the first part just means the phi 1 will be from will vary from 0 to minus t2, right? So we have the first one here with the click point here. Here will be the phi 1. Okay, and the other one will be, the phi 2 will be like this. And here we have the phi 2 omega. Okay, and then when we combine this both this one together, then we will have here is the final one. Sorry, I draw a little bit not very nice here. Yes, like this. Okay, so this one will be the phi omega equal to phi 1 omega plus phi 2 omega. Okay, and it's the same here. L omega equal to L1 omega plus L2 omega. See, so this is the both diagram of the system with this transfer function. All clear? Any questions?
Teacher,
Yes.
I have a question. This they are the linear equation, so we can plus for example, from 1 over T2, we have equation with angle E40 minus 40 decibel over decad. So it is em muốn hỏi là đây là các đường tuyến tính nên mình có thể cộng các đường vào với nhau ở đây, nên có độ dốc là trừ 40 decibel trên decad ạ.
Bởi vì hai cái đường tiếp tuyến của hai cái nhánh đồ thị ấy, khi mà omega tiến ra vô cùng ấy, đúng không? Thì nó đều là cái đường tiếp tuyến mà có cái độ dốc là trừ 20 decibel, đúng không? Thế thì khi mình cộng đồ thị vào thì nó sẽ ra một cái đường tiếp tuyến là có độ dốc là trừ 40 decibel thôi. Đúng, và đúng, nó là đường thẳng, đúng không? Vì mình đã biết cái đường tiếp tuyến là đường thẳng, cho nên là mình có thể cộng hai cái đường tiếp tuyến đấy lại với nhau, xong rồi mình cộng đồ thị với nhau thôi. Hiểu nhá. Cái phương pháp này bạn nhìn thấy cái cách vẽ của cái đồ thị đặc tính tần số này ấy, là bạn cộng đồ thị của từng cái đồ đặc tính tần số thành phần vào với nhau, đúng không? Cộng đồ thị đây đúng cho cả trường hợp là biên độ và góc pha, đúng không? Bởi vì theo cái công thức này bạn thấy đây này, đây cái đồ thị đặc tính tần của hệ thống này thì bằng tổng hai cái đồ thị đặc tính tần đây, thấy không ạ?
Giờ có.
Đó nhá. Ok. Okay, so you can do the same for different type of system. Okay. So I want to introduce you a special case of the system that we will use quite quite often in the future here. That means we have we have one system. We have example, right? We have GS equal to 1 plus T1S over 1 plus T2S. Okay. And suppose that we have T1 greater than T2. Okay. Then the same for this equation here. You will see that you will see that here we have L omega will be equal to this one instead of you see here the equation here we already have over there, right? Okay. L omega will be that means okay, J omega will be 1 plus T1 J omega over 1 plus T2 J omega. Okay, that means we have L omega will be equal to 20 log of 1 module 1 plus T1 G omega minus 20 log of 1 plus T2 G omega, J omega, correct? And the phase omega will be equal to, it's still the sum of the phase, okay? Equal to phi 1 omega minus phi 2 omega, all right? And phi 1 omega is equal to arc tan of T1 omega, and the phi 2 will be equal to arc tan of T2 omega, right? Okay. And then we have okay, and here, from here we see that you know, we try to draw on the diagram this the diagram of this one, okay? So I will try here. The first one is a magnetus. Okay, we still have T1 here, 1 over T1, because we also assume that the T1 greater than T2, okay? And here we assume that we have 1 over T2, here is omega, and because we see here we have the 20 log 1 plus T omega. Sorry, this actually should be, move a little bit down. Okay. So you see the line 20 logs 1 plus T1 omega will be like this. When omega goes to 0, it's still this straight line. Okay, when omega goes to infinity, is instead of minus 20 decibel per decade, it will be plus 20 decibel per decade, right? Here, yes, and then you see, and then the second one will be, and here is the exact curve of this diagram. See, then the second one will be the same for asymptote lines. Here we have this one, and for this one we will have minus dB per decade. Here we have 20 dB, 20 dB per decade, and here we have minus 20 dB per decade, right? And the exact curve of this L omega we also have here. So the first one is here is L1 omega, and the second one here is L2 omega. Okay, we write here L2 omega, right? Then we also do this diagram, combination of these two diagrams in one. Okay, then we have the final one will be goes like this. The first state is go like this, and then the second state is will go like this, right? But when it's meet here, and then because here we have the 20 decibel per decade plus minus 20 decibel per decade, that means here we will have a straight line again. I will, yeah, the straight line again. Here is the 20 dB per decade. Yeah, right. And it's a asymptote lines of the curve, and the exact curve will be like this. See, so this will be L omega equal to L1 omega plus L2 omega, right? Minus L2 omega. Sorry, plus L2 omega. Sorry. See, because L2 omega is the minus 20 logarithm of 1 plus T2 J omega. Understand? That means here we have at the first stage of that means when the frequency is smaller than 1 over T1, so the input and output have the same frequency because the amplitude equal to 1 here. Okay, but when the frequency is in the middle from 1 over T1 to 1 over T2, then the output will be amplified by a gain like equal to this portion. Okay, the gain of this one here is this line, and then at the higher gain, higher frequency, okay, then the output and input, the factor of the output magnitude and input magnitude is constant again, okay, but it's not of course it's not one like this, okay. And now we draw the phase diagram for this system. Okay, it's very interesting here. So that means here, if we look at the magnitude diagram, we will see that, okay, at the low frequency and the high frequency, the input and output, we can say input signal and output signal, we can say the output is proportional to the input. Okay, the magnitude of the output will be proportional to the input, and this is the factors here almost constant. Okay, but for low frequency, it have the factor equal to 1, and the higher frequency is have a factor equal to, of course, greater than 1, and we can calculate this one. 1 over, that means here is T2 over T1, right? Or T1 over T2. Yes, T1 over T2. Okay, the magnitude of this one will be T1 over T2, right? And of course 20 log of T1 over T2. Right? Yes. Yeah. Okay. And the phase diagram will be very interesting. You will see here the same for the first one, the previous example. Okay. Then we have here, for example, minus p over 2 and minus p here. No, we just have minus p over 2. Oops. So I'll draw is a little bit bigger here in order to. Here we have minus p over 2. Here we have the frequency here. We also have the frequency here. Right, and the first one is going to come from here, because the phi one is arctan of T1 omega. Okay, T1 omega, and this one will come from 0 to, with a plus sign. Okay, and this one will come from 0 to p over 2. Oh, sorry, this system will be here. We should draw the different action here. Okay, and here is the, all right. For the first one, we will have the phase, okay, vary from zeros to p over 2. Right, here we have the phi 1 omega, and the second one is we have the phase vary from 0 to minus p over 2. Okay, that means we have the phase here. Okay, we have here the phi 2 omega, and when we combine these two into one, okay, then we have here the first part go with this, and the second part will be will go with this. See, here we have the phi omega, equal to phi 1 omega plus phi 2 omega. Okay, we call this here plus phi 2 omega here. You see, and this phi 2 may equal to minus octane, right? So here is a whole diagram of this system. Okay, in which assume that the T1 over greater than T2, and we can see that here in the most case, the phase of the output signal will be, go beyond the phase of the input signal. That's why we call this system as the phase-less system. Okay, phase-less system. Okay, and the system with this condition we call it lead system. Okay, lead system. Because you can see when we add that means when we add a lead system into open loop, okay, the magnitude of the whole system change not not significantly, but the phase of the output will be pushed into leading the phase of the input signal, okay, with the the amount of p over 2, okay, in the yeah, right, and the same one, okay, the same one if we have the GS equal to still 1 over T1S over 1 plus T2S, but now we assume that T1 smaller than T2. Okay, this system is we call it lag system. Okay, lag system, and okay, lag system, and it also have similar phase both diagram of the previous one. You can do it by yourself at home, but I can write here quite fast. Okay, here is 1 over T1 and 1 over T2, 1 over T1 here, and yes, yeah, and we have the for this one we have plus 20 decibel per decade here, and for this the first one we have the plus minus 20 decibel per decade here. Okay, and the final one we have here, you see here, it goes to this line, and then at this point it goes to straight line again. All right, that means the exact lines will be like this. Okay, here is the L omega. Okay, and the phase, when we look at the phase, and it's almost the same as the example before. That means from the magnitude point of view, we can see that the output is almost proportional to the input. Okay, but when we look at the phase, it's very interesting here. You can see now we have here P over 2, here's minus P over 2, and we can see that here will be, you see, all right. Here is the phi1, all right, and here is a phi2 omega, and of course when we combine this one together, we will have this one. Right? Sorry, it's not like this. This one again, and then we will see is here phi omega equal to phi1 omega plus phi2 omega. Okay, and this one we call, because of this part, and then we call phase lag. That's why this system will be called as the lag system. Okay, lag system. And because you see from the magnitude point of view, okay, this not change the magnitude of the input and output very much. That's because the input and output is proportional together from magnitude, and but from the phase point of view, you will see that the output will be shifted related to the input. Okay, depend on its phase lead or phase lag, it will be shifted by, you know, a value of minus p over 2 or plus p over 2. Okay. So that is the both diagram of some you know, basic system. Okay, and we can use, okay, we can use, so we goes to I will open the new page for this week. Okay, we have the week 13. Today is 15, right? Correct? Yeah, yes, right. And we also try, now we try to use the frequency response of the system in order to analyze the stability of this of the system. Okay.
Teacher,
Yes.
I have question previous slide.
Previous, yes, one. Yeah.
I wonder
Yes, go on.
uh, as as the L omega is 0, so why high gain is 1? I don't understand it.
L omega equal to 0.
Yes.
Y gain is 1, right?
Yes.
Because L omega is a 20 log of amplitude, and when log equal to 1 to 0, what is the variable? When log x equal to 0, then x will be equal to what?
This variable is 0, is 1.
Yeah, that's why. See?
And again, high gain is the magnitude of g j omega.
Yes. You see here, for example, this case, at the high frequency, the gain will be, T1 over T2. Okay, and the same here, right?
Okay, thank you very much, teacher.
Yes. You can easily, you can easily verify this um, this diagram, okay, or this diagram with the MATLAB function. You can simulate the signal, the input signal, and you change the frequency of the input signal, and you can see the, um, the amplitude of the output signal will change according to this diagram. Okay. Um, yeah, I think that we will have a short break now, and then I will open the MATLAB program and show you how to verify this diagram. Okay.
Yes, sir.
Yeah. Okay. So it's before we go to the new, um, the new lesson. We have stop break now, and we come back on 8:15. Okay.
Yes, sir.
Okay, you come back to and we continue the class. I already opened my MATLAB program in order to to simulate the input the behavior of the lead lag system here. Okay, and I will show you the my MATLAB window. And in order to do that, I will introduce you a new tools of MATLAB program. We call it Simulink. Okay. Here is the Simulink windows. Okay. I will open a new model. Just mean new system. Okay. Yeah. And I will open the library browser in order to have some basic elements that we can use here, and we try to a transfer function. Where is this transfer function? Yeah, for a system. Okay, we will define it as the numerator will be, suppose that we have the T1 greater than T2. Okay, for example 100 and 1. That means 100s plus 1. Okay, and the denominator will be 10. Yes. Okay. And then we will give it the input as a browser, the input source, and I will use the signal generator here. Where is this? Sine waveform generator. Suppose that we will have we know we can use this another one, which is here sine wave here. Okay. And at the output, we will use. I will use a scope. That's been here. Okay, and then we have the input. The board diagram of this system we can draw is here. For example, system GS equal to TF of numerator is 100 and 1. Denominator is 10 and 1, right? And use the board of GS in order to draw the board diagram. You see here, you see the same as we draw before by hand. Okay, that means the amplitude goes from here to here, and the phase, the phase goes from this way, right? This is the real phase lit system. Okay, And we will try to, you know, to verify this both diagram by, you know, using the simulation here. We already have this one. Where is this? Here, this one. Correct. Here is a both diagram. Here is a simulation. And for example, here we have the frequency is when we have the frequency smaller than here radian per second. That means frequency here, for example, we try to simulate with the frequency of 0.0002 radian per second. Okay. All right. And we try to we'll try to run it. Wait a little bit. Yes, it's finished. Now we see the output. We will here is the output. No, because the frequency is too small, so we have to increase the, you know, increase the time here to 100 seconds. Not enough. 1000 seconds. Not yet. Yeah, yes, that's right. Too many. Yes, okay. No, still too many. Okay, so we want to compare the input and the output. So I will want to add signal 2, and I want to connect this one here. Yes, then we can have, yeah. Okay, so the input will be sine wave will be the blue one, and the output will be the yellow one. Yes, and you can see that the frequency of this both are almost the same. Okay, almost the same, and the phase, yes, the phase of the output, you can see the phase of the output is lead the phase of the input about, here we can see it's about few degree here, right? It's very small. Okay, here the frequency of 2 is about this frequency of 2 here, this one. Sorry. Sorry. Yeah, almost this one. Okay, this point, and then we see that the amplitude is almost the same between the input and the output, right? And yeah, and but the phase, the input will be lead the sorry, the output will be lead the input about how many? 10 degree. Okay, 10 degree here. See clearly? And if we increase the frequency here, okay, to the point about here, that means about frequency is about 0.3. Okay, 0.3, and we can see 0.3 radian per second. Okay, and we try to run again. This time because the frequency is much higher than before, so you see here the input, the phase lead of the input is clearly advanced. The output, the phase lead of the output is clearly advanced. The input signal by about 50 degree, okay, 55 degree, and how to see it? Yeah, this one. Yeah, that's right. It's easy to see here with this one. You see, the input here is the sine wave here is a blue one, and the yellow is the output signal. Okay, and the output is advanced. The input by almost 55 degree. See, and the amplitude you can see here. Amplitude is the here we have the amplitude about yeah, 10 dB. 10 dB just mean 20 log equal to 10. 20 log equal to 10 just means the output will be how many times? 5 times, about like this. Okay. So and we try to another point of frequency about this point, for example. Yes.
I thought I have calculated, and I thought the gain is almost 3.
Almost 3. Yes. You see the amplitude here, and the amplitude of the output. I can use some tools here, measurement tool. Where is this? We don't have any here. So we see here the amplitude is about 3, right? Of the yellow one. See? Here, the amplitude is almost 3. Okay? Compared to the amplitude of the input is 1. Right? So yes. It's correct with the same as you calculated, right?
Yes, and I have calculated 3.1.
Yes, 3.1. You see here? You can easily see that. And I will try to the next one. Okay, the next one will have the frequency of, I will try this one, 1. Okay, 1 radian per second. And you can see the magnitude is 20 dB. That means the output should be 10 times the input, right? So yes. 1, and I will reduce the number here because the frequency is the moment. I have a Okay, I will try to reduce the number here because we don't need still too many. One, still too many. It should be about 20, 50. Okay. Okay. 1 radian per second is too big. Yeah, it's okay. Here, 20. Yeah, it's okay now. Okay. Now you can see here is the almost 10 times, right? As I said before, because we see here the magnitude is about 20 decibel. 20, that means the log is equal to 1. That means x equal to 10, right? And the frequency is about, at this point, the frequency is about 5 degree, right? 5 degrees. That means the phase shift between the input and the output is very small, about 5 degree. And you can see here clearly that the input and output have the same frequency here. Okay, the same phase, right? So that means here we already test, simulate the behavior of the system with the different frequency of the input. We keep the amplitude equal to 1, and we change the frequency from, here this one it's 0, 002 radian per second to the 0.3 radian per second and to the 1 radian per second, and we see the different output input relation. Okay, at the frequency, the low frequency, we have the input and the output have the same amplitude, but the phase is about 10 degree. Okay, and at the highest point here, about around this point, we have the input and output magnitudes about 3 times as Mr. someone here calculated, and then the phase is about 55 degree. Okay, and the higher, when the frequency goes higher, then we come back again. Okay, the phase list reduce as the phase, the difference between phase the phase between input the up and the output reduce, and we have the magnitudes become to a constant. Okay, that means the output will be about 10 times the input. Okay, and you can easily change this one to the phase lag by changing this one, the same phase list and lag. Okay, and now if we simulate it again, you can see the opposite, the same, no, but the amplitude now will be reduced about 10 times. See here, right? The blue one is input, and now the yellow one is the output, but the phase is still the same. Okay, and if we come back to the point here about 002 radian per second. Okay, of course we're going to increase the time, simulation time here. You can see here again, right? The input and the output have almost the same magnitudes, but the phase is about, this time the output is go behind the input. You see, behind in the face with the input. See, so now you already know about the both the frequency response of a system. Okay. Any questions here?
Em thưa thầy, sao cái
Yeah.
đường phase nó lại không thể đạt đến đường 90 độ ạ? Bởi vì em thấy trong hình thầy vẽ là nó có thể gần tới đấy ạ.
Bởi vì là cái khoảng cách này của mình này nó chưa đủ lớn. Đây, ví dụ em cho nó xuống đến khoảng 1 này chẳng hạn này. Đây nhá, bot diagram đây nó ở bên này. Ta vẽ nó ở đâu nhỉ, đây, đúng không? Nếu em cho cái này nó vì ta nhớ là cái đường ta vẽ ở trong đấy nó chỉ là đường gần đúng thôi, đúng không? Đấy, ví dụ cái này số 1 chẳng hạn này thì có lẽ là nó sẽ đủ, hoặc là 0,1 đi chẳng hạn. Đấy. Thế thì lúc này khả năng là nó sẽ đủ cái 90 độ. Đâu nhỉ? Đây. Đây, thấy chưa? Đấy, nó tiệm cận đến 90 độ rồi đây này. Bạn thấy không? Đấy, nếu mình vẽ tiếp ra, ví dụ như là cái này chẳng hạn, này cái này tăng cái này lên nữa, đúng không? Thì các bạn sẽ thấy cái đồ thị đấy nó đạt tới 90 độ được. Yeah. Ok.
Dạ vâng.
Vì ta nhớ đây là trên cái thang tần số đây của chúng ta nó là thang gọi là số mũ của 10, đúng không? Đấy, thang logarit này. Đấy, số mũ của 10 đây là 10, đây này, cho nên là cái khoảng tần số này nó phải đủ lớn thì nó mới tiến tới cái đường tiệm cận ấy. Đó. Đó. Ví dụ như đây mình cho cái này lên khoảng 10.000 chẳng hạn. Đấy, nó tách hẳn nhau ra. Đấy. Thì lúc đấy các bạn sẽ thấy cái rõ ràng cái vị trí cái đường tiệm cận. Đây. Đâu rồi? Nó chỉ vẽ từ 10 mũ trừ 1. 10 mũ trừ 1 này. Thế. Sao bây giờ nó chỉ vẽ có một nửa thôi? Nó không vẽ hết ra cho tôi. Đó. Đó. Yeah, đã giống như là mình vẽ trong trên giấy kia chưa? Ok.
Dạ vâng, em cảm ơn thầy.
Ok. Đó thì cũng là nhân cái nội dung này thì tôi giới thiệu với các bạn luôn một cái công cụ. Đấy là cái công cụ gọi là Simulink. Thực ra nó cũng vẫn là cái mô phỏng của cái hệ thống điều khiển thôi. Chỉ có điều là bây giờ thì nó vẽ cái hệ thống điều khiển đấy bằng một cái sơ đồ khối, đúng không? Trên một cái sơ đồ khối như thế này thì nó trực quan hơn cho chúng ta. Đó. Đấy, chúng ta có thể dễ dàng quan sát được xem là cái hệ thống của chúng ta nó như thế nào. Nhá. Ok. Rồi. Tôi sẽ tắt cái này đi. Okay, now we come back to our lesson. Wait a moment. Now we go to the part that is the stability analysis using the frequency response. Okay. Stability analysis with frequency response. Yes. And uh, with frequency response, and the criterion we use for this part is this analysis is the Nyquist stability criterion. Okay, we call it Nyquist stability criterion. Okay, criterion. Now we consider the control system. Feedback system. Like this. Okay. That means here we have the GS, and on the feedback line we have the HS. Minus. Okay. Then the closed loop. Okay, this means the closed loop. Transfer function. Okay, is a GKS is equal to GS over 1 plus GS 8S. All right. Okay, and the poles of closed loop system. Root of characteristic equation. Okay, 1 plus GS multiple with HS equal to 0. Okay, and in order to um, um, to analyze the stability of this system, we draw a Nyquist curve. Okay. Okay, Nyquist curve is the function of g omega multiplied with h g omega. Okay. And when we plot this, we call it the Nyquist diagram of, or Nyquist diagram, not curve, of open loop system. Okay, we call it Nyquist diagram, or the magnitude phase. It diagram. It's actually it is a magnitude phase diagram of open loop system. Okay, and when we draw it on the S-plane, okay, sorry, on the um, um, imaginary and imaginary plane of the g omega, then we can we call it the Nyquist diagram of the open loop system. Okay, and we try to okay, then we have a Nyquist criterion. Okay, Nyquist with no, not y but I. Okay, we write a set equal to n plus p. Okay, and z set is the number of zeros of 1 plus gs multiplied with hs in the which is in the uh, right half of S-plane. Okay, and the p is the number of poles of gs multiplied with ss in the right half S-plane. Okay, and the n will be the number of clockwise clockwise encirclement. Of Nyquist diagram. around so -1 plus 0 g0 point. Just means the point -1 on the real axis of on the S-plane, okay? And okay, that mean here if GS, if the open loop system with model of GS multiple with HS have no or has no poles in the right half S-plane. That means the closed loop system will be stable if the Nyquist diagram do not encircle the -1 plus g0 point. Okay, just mean here, for example, if we try to we draw the diagram for here is a imaginary real and here is a imaginary axis, and here is a point of -1 -1 plus 0 j. Okay, if we start with the omega is equal to 0, and if the Nyquist here, for example, times when the omega here, and because this one is not encircle the point minus, so this case, okay, the closed loop system is stable. Okay, but other case, for example, here with the same or when we have, for example, this one omega equal to 0, and when it go, for example, like this, goes to, or it goes like this, okay, to 0, for example, then because the point -1 plus on the real iso here is encircled by the Nyquist diagram. So the closed loop system. Unstable. Okay, unstable. And okay. And it's a case, the first case that the system have, if the open loop system have no poles in the right half S plane, okay, and okay, and then the other case is if okay, if the open loop system have has p pole uh, p poles on the in the right half S plane. Then Okay, then if the suppose that the set in the equation before is equal to zeros, that means the n equal to z minus p. Okay, and if z suppose hay là assume that z is equal to 0, that means n should be equal to minus p. That means the Nyquist diagram in cycle the point minus 1 plus g0 n times counterclockwise. Okay, then the system is stable. And if this this condition is we meet, we can have this condition, then the closed loop system is stable. If not, then the system is not stable. Okay. And if the case, okay, the third case is if there are one or more clockwise encirclements of Nyquist diagram, over around point minus 1 plus g0, then the closed loop system is unstable. Okay, unstable. Now we can do some example of it. Okay, example of it. Suppose that we have for example, okay, we have the we have the control system or closed loop control system like this. Okay, we have here the same as case that we use the root locus. Okay, and here we have gs equal to 1 over t1s plus 1 t2s plus 1, for example. This one. Okay, then we draw the Nyquist diagram for this. Okay, draw the Nyquist diagram for this, and we will have here okay. Is when we draw the Nyquist diagram for this open loop system, then we will have the diagram like this. It start from 0 here. The point -1 should be here. All right. So the Nyquist diagram will goes like this. Okay, and here is will come to here. That means here omega equal to 0. Is the here omega equal to infinity, and in fact it will have the opposite part. When we come here omega equal to minus infinity and goes back to 0 like this. Okay, we can draw this one complete Nyquist diagram like this here, and we see that okay, this system is not inside the point because the open loop system have no points on the right half S-plane. Okay, and the Nyquist diagram is not inside the point -1. That means the closed loop system. Okay, from this Nyquist diagram we can say that okay, closed loop system is stable. Okay, now I will reopen my MATLAB program and to show you how to draw the Nyquist diagram for this system. Okay. I will show you here. My MATLAB again, and I will define the GS equal to TF of this case 1 over for example T1 equal to I will define S equal to TF of transfer function of S. Okay, and we will define T1 equal to 10 T2 equal to for example 20. Okay, and K, for example, I will suppose K equal to, for example, 2, for example. Okay, and then we have GS 1 equal to, K over T1 multiplied with S plus 1. Okay, sorry, T2. Right. I will use this set. Okay, you see, then we use Nyquist comment or Nyquist function to draw the Nyquist diagram of this GS1. See here, and we see the point 0 here. See clearly, and I want to talk to you. Yes, like this. Okay, and what try to, you see that the system will be, stable with every value, because it's not from when the frequency goes from minus infinity, minus infinity to infinity. Yeah, frequency is minus now minus infinity here, and we goes to all the way to the zero, frequency equal to 0, and all the ways to this. Okay, here is when the system goes from this way, we see that the whole Nyquist diagram not encircle the point -1 here. That means the closed loop system is stable. Okay, we try to with different value of k. Okay, we suppose that maybe if we change the k is, for example, to 20. Okay, and then we have the GS2. Okay, and yes, sorry, GS2. I want to yeah, see here the GS2, when we increase the value of k, you see it's a red one here, and compare to the Nyquist diagram of the GS1. Okay, so system. You can see here both case, the Nyquist diagram have the same shape, but of course different. The size is different. Okay, but it's still not encircle the point -1 here. Okay, and another case. Okay, I will try this one. Now is we add here GS3 3 here, and we add here one poles on the real on the imaginary ISO. Okay, then we see GS3 with S on in the denominator. Okay, and then if we try to draw the Nyquist diagram of this one, okay, now we see that when the system come from, we see that here, how to zoom it into this one here. The value of k, the Nyquist diagram now will depend on the value of k. In this case, you can see here, okay, when we go from infinity here, so the point -1 always on the right hand side of the Nyquist diagram. That means the Nyquist diagram is encircle this point. clockwise. So the closed loop system is unstable. Okay. We try to verify it by GK3 will be equal to feedback of GS3 1. Yes, and we see that here very clear that the GK3 have a negative poles. Poles at it will have poles at positive S-plane, half positive half of S-plane. Okay. Here we see, for example, impulse of GK3. That means closed loop system. Okay. Where is this? I want to have to open another. Yes, you will see here. Okay, here is the impulse response of the system, and we see clearly that the system is unstable here. Okay, or we can do like this. We can see that, okay, the system here we have poles of GK3. Then we also not poles. Sorry. Here we see there are two poles on the right half plane. Okay, that means the closed loop system is unstable. It's the same conclusion that we meet with the Nyquist diagram here. But if I change, I close this one. If I change the k value now equal to, for example, 1, for example. Okay, I don't know how the value of k that makes the closed loop system will be stable again, but I will try it here. Okay, and GS3 equal to now, right, and Nyquist of GS3. Then we see, yeah, we also see that, and we look closer at the point 0, 1 here. You will see that the system will encircle the point. See here? Okay, maybe you still not see, and I will try to make you see more clearly here. Yeah, that's right. Okay, and we see that when the omega goes from minus infinity to infinity, the system goes into this with this lines, this contour, right? And clearly that the Nyquist diagram will encircle the point -1 once, right? So according to our conclusion criterion here, we say that because the open loop system have one point on the right half plane, okay, equal at s equal to 0. That means the Nyquist diagram should encircle the the point -1 once. Okay, once. And here is encircle once. So I will try to find the closed loop transfer function, and we try to poles. Okay, check the poles. What is it? Why is still clockwise? Yes, clockwise. Sorry, I have mistake somewhere.
Em chưa dạy. Em tưởng close transfer function nó khác chứ ạ, chứ không phải là k trên T1 nhân S cộng 1 nhân với T2S cộng 1, bởi vì em tưởng đây nó có feedback ạ.
Thì đây mình đang tìm closed loop function đây còn gì nữa.
Thay vì mình dùng hàm transfer thì mình dùng hàm feedback là thầy.
Feedback đây là thực ra là một cái hàm để tìm cái closed loop mà khi mình có feedback thôi. Đây đúng rồi này. Đúng rồi này. Cái này đúng rồi. Vậy tại sao nó vẫn có phones on the right half plane? Vẫn unstable mà. Tại sao Nyquist của nó lại tại sao Nyquist lại vẫn nó vẫn bao điểm này? Mình có nhầm chỗ nào không đây? Đây là cơ từ trừ vô cùng. Đến vô cùng. Đến vô cùng. Đúng không? Sao nó lại thế nhỉ? Trừ vô cùng này. Đi qua đây này, vào điểm này một lần này, đến vô cùng. Wait a moment. Once and twice. Yes. nó lại là bao 2 lần cơ. 1 này và 2 này. Ok, vậy thì nó phải có 2 ở right half plane. Nó vẫn không ổn định. Small k nữa xem nào. Đó. K equal to 0.1 and GS 3 here, GK here. Yes, Nyquist GS3 now. Yes. Okay, now this K is not in cycle and not the point -1. Okay, then the system is a closed loop system is stable here. Okay, then we hold up GK3. Yeah, we see all 3 poles are on the left half plane. Okay, left half S plane. So the closed loop system is stable. Okay, with the Nyquist diagram we see here, when the system come from minus infinity to plus infinity, we see it goes in this direction and it's not in cycle the point -1 in the yeah, it's not in cycle the point -1. Okay, so the system is stable. Closed loop system is stable. Okay, before we see yeah, I made a mistake here. Before, when the k equal to 1, okay, so the system, we have the system here and GS3 and the GK3 and Nyquist here. The system encircles the point -1 once. Okay, but we have only we don't have any poles of the open loop system on the right half plane. I have made a mistake because we have here S equal to 0, not another case. Okay, so okay, that is the way to use the Nyquist diagram in order to analyze the stability of the closed loop system. Okay, and yeah, this method is quite common with the old-fashioned engineer. That means the engineer from the year about 20 or more years ago. They usually use this criterion in order to analyze the stability of the system. Nowadays, when we, with the help of the computer program like MATLAB or the equivalent software, normally I see the less user use this method to analyze the control of the stability of the system. Instead, we can directly find the stability of the system using the poles of the closed loop system. Okay. So that is for today. Do you have any questions?
GS3 là open loop system hả thầy? Transfer open loop hả thầy? Đúng không ạ?
Cái gì cơ?
GS3 là open loop hả?
Đúng rồi, đây nó là cái open loop đây này, cái mô hình hàm truyền của nó đây. Bạn nhìn thấy không?
Dạ có. Vậy
Nhá. Thế khi mình mà nó có cả hệ số k ở đây rồi đúng không? Thế khi mà mình dùng cái feedback này thì mình sẽ có cái close loop đây, đúng không? Thế thì trước kia khi mà dùng cái tiêu chuẩn Nyquist này ấy, thì các bạn sẽ chỉ vẽ cái đồ thị Nyquist của cái open loop này thôi. Sau đó bạn xem luôn trên cái đồ thị đấy, bạn có thể kết luận được về cái tính ổn định của cái hệ kín ở dưới này. Đó. Đấy, ta có thể kết luận được về cái tính ổn định của nó. Thế nhưng mà như tôi vừa nói đấy, đây như ta vừa làm đấy thôi, đúng không? Nhá. Ta nhìn thấy đây rõ ràng là cái đường đồ thị đây nó bao cái điểm -10 đây này. Đúng không? Đấy, thế mà trong hệ hở thì không có cái điểm cực nào nằm ở bên phải trục ảo cả. Nhá. Thế thì chứng tỏ là gì? Chứng tỏ là cái hệ kín này của chúng ta là sẽ hệ kín không ổn định. Đúng không? Thế trường hợp khác khi mà ta thay đổi cái giá trị của k đi, lúc nãy ta thay đổi giá trị của k đi, đó, tức là cái đoạn đâu nhỉ, k bằng 0,1 đây này, được chưa? Đâu nhỉ? Đó. Đấy, khi mà ta thay bằng cái k bằng 0,1 đây thì ta nhìn thấy cái vẫn cái đường đồ thị đấy, nhưng bây giờ nó không bao cái điểm -10 nữa. Đúng không? Vậy thì mình có thể kết luận là hệ kín ổn định. Thế và lúc nãy ta cũng kiểm tra luôn là cái hệ kín của nó thì có cả 3 điểm cực nằm ở bên trái trục ảo ấy, các bạn nhìn thấy không? Đây này, lúc nãy ta vừa kiểm tra đâu đây, đây này. Được chưa? Nhá. Đây nó là một cái tiêu chuẩn mà gọi là tiêu chuẩn hình học. Đấy, thì người ta có những người thì người ta thích sử dụng cái tiêu chuẩn hình học để khảo sát tính ổn định của hệ. Đấy. Nhưng cũng có những người thì không thích như thế, đúng không? Thì tùy chúng ta thích dùng cái phương pháp nào thôi. Đó. Thế trước kia là cái đồ thị Nyquist này là chúng ta có thể vẽ được. Đó. Cái đồ thị Nyquist này là chúng ta có thể vẽ được bằng thực nghiệm, tức là giống như lúc nãy ta làm thử nghiệm ấy, ta vẽ ta cho cái kích thích cái tín hiệu đầu vào bằng một cái hàm hình sin, ta đo cái tín hiệu đầu ra, ta so sánh cái biên độ và góc pha, thì từ đấy ta tính được cái g omega tại cái tần số đấy, đúng không? Tại điểm tần số đấy, thì nếu như mà ta cho cái điểm tần số đấy nó thay đổi thì có phải là ta vẽ được cái g omega khi omega chạy từ 0 cho đến một cái giá trị đủ lớn, đúng không? Hay nói khác là ta vẽ được cái đồ thị Nyquist này của hệ hở. Đấy, chính vì thế cho nên là và từ đó ta mới kết luận về cái tính ổn định của hệ kín luôn. Đấy, thì đấy là cái thời xưa khi mà cái công cụ mà trợ giúp bằng máy tính này của chúng ta nó chưa phát triển, thì người ta làm thực nghiệm, người ta làm như thế. Đó. Tức là từ những năm thường những năm 90 trở về trước ấy, thì người ta sẽ làm như thế nhiều. Thế nhưng mà sau này khi mà cái công cụ mà máy tính, phần mềm trên máy tính nó phát triển ấy, thì cái công cụ thì chúng ta tìm trực tiếp cái điểm cực của cái hệ thống nó dễ dàng hơn nhiều. Chính vì thế cho nên là cái việc mà sử dụng cái đồ thị Nyquist, cái tiêu chuẩn Nyquist này nó càng ngày nó càng ít đi. Chỉ có điều là trong chương trình nó có nên tôi vẫn phải đưa vào thôi. Các bạn hiểu chưa nhỉ? Any questions?
Teacher,
Yes.
I just want to ask you about the midterm exam, and a few minutes later I will have it, right?
Yes.
Yeah, thank you.
You will have it on 10:30, I think. I don't remember what time is it. Okay.
Yes, 10:30. Okay, I will be there.
So wait for it. Okay, don't miss this time.
Yes, yes. Okay.
Okay.
Teacher, the exam will be in the assignment, right?
Yes.
Yes.
It's assignment when the teams will notify you when the time is coming. Okay.
Yes, yes. Okay.
Okay. So if you don't have any more questions, then I will stop my class for today here.
Dạ thầy, Có câu
Yes.
hỏi cuối là cái này quiz này nó chính là nó vẽ cho cái open loop ạ.
Từ nãy giờ mình vẫn nói là vẽ đồ thị Nyquist của hệ hở mà, đúng không? Mình vẽ đồ thị của hệ hở nhưng lại kết luận về tính ổn định của hệ kín, hiểu chưa nhỉ?
Dạ vâng.
Nhá.
Em lại vậy trục tung là biên độ rồi thầy.
Đó, trong cái đồ thị Nyquist này là nó vẽ là trên đồ thị trục thực trục ảo chứ. Trục thực trục ảo, tự phần thực phần ảo của cái hàm g omega ấy, của hệ hở ấy, đúng không? Thế nếu mà tính từ tâm trở đi ấy, mà đến một cái điểm bất kỳ trên cái đường đồ thị ấy, thì bạn mới có là cái vector đấy, ví dụ như là đây, ví dụ như là cái điểm từ tâm này đến một cái điểm bất kỳ trên đồ thị đấy nhá, đây này, bỏ cái này đi, đúng không? Đây, ví dụ đến một điểm bất kỳ trên đồ thị đây, thì bạn sẽ có là nếu mà tính từ tâm ấy, thì cái vector đấy, cái độ lớn của vector đấy nó là biên độ, thế còn góc của vector nó là góc pha, thấy không? Đây này, ví dụ biên độ là
Share slide thầy.
hả?
Màn hình của em chưa thấy gì.
Đây tôi vừa tắt đi mất rồi. Đây là đây, vừa bật lại đây, nhìn thấy chưa?
Chưa.
Bây giờ thấy chưa?
Thế ạ.
Đấy nhá, thì có phải bạn cái điểm này bạn nhìn thấy là phần thực này, phần ảo này, đúng không? Và tần số này, thấy chưa? Thế nếu mà bạn nối cái vector mà từ cái tâm của cái, tức là điểm 0 ấy, đến cái điểm này, đấy, thì bạn sẽ thấy là cái độ dài của vector đây chính là gì? Là biên độ của nó, đúng không?
Dạ vâng.
Đấy. Cái này giống như buổi hôm trước ta nói ấy.
Dạ vâng.
Ok. So, goodbye.
Em chào thầy ạ.
Em chào thầy ạ.
À.
Em chào thầy ạ.
Chào thầy ạ.